Let's continue. Okay, let me open the table of content first. Okay. Currently we are still on chapter 8. Patching introduction here. Still on homework simulation section. Let me open that. Okay, wait. Okay. We are still in this section, homework simulation. Basically, checking out the simulation script to check how translation virtual to physical trace works with linear page table. So we are learning about patching technique with linear page table. We already checked the question 1, question 2, and then now we are in the question 3. The last time we tried out this configuration, but we haven't finished yet. So instead I am curious about this one. Is using what is it called? Orbit-wise operation always the same as the addition, right? Let me open my terminal emulator here. Not necessarily decimal addition, I guess. So check if addition is a bitwise XOR with carry bit. Yeah, I'm kind of curious about this statement, I guess. What does it mean by carry bits? Let me check. Okay, and then let's just do this, I guess. Carry bit, okay. I think, okay, the page size is 4K. If it is 4K, then is it gonna be this one? Okay. The 12 bit there. Think something like this. I mean should be left shift. Wait, I kind of forgot. The offset is virtual address, right? Virtual address. Okay. Virtual address with masking. Page size, page max. Okay. 1495, I think. Something like this. Okay, this is the offset. And then adding this. Oh, wait. Virtual page number 3. This one. Oh, this one. Okay. Looks like, yeah. I forgot to get the virtual page number here. Okay. How do I get the virtual page number again? Okay. How many F is this? 3, 6, 8. Oh, okay. 8. Alright. Yeah, getting the, what is it called? Getting the virtual page number max here with the complement of page max. Okay. Alright. Right. Okay. And then we add that to the masking. Right. Let's see if 12. Okay, 3. Alright. It is 6. Okay. So we got think we got this. No. This 25. Okay. Oh, right. 6 with this one with 6 is the virtual page max, right? Oh, no. 6 is the frame, what is it called? The page frame number. So I need to do this, left shift to get the base of the page frame, and then adding that to with offset. I mean, what is the offset again? this one 500. Okay, yeah, we are adding something like this. Is it 0? Oh, okay, interesting. Let me not that. Okay. Alright. Oh, interesting, I guess. This is 15. Okay, maybe something like that. Okay. And then trying to use n here and bitwise operation. Okay, 0. Oh, okay, interesting. If I put this like this, okay, 16, 9, 37. Oh, this is not 0. Is it gonna be? Yeah, I don't think this is the addition of this one with this one. Oh, I mean, alright. No. Okay. Yeah, it is different. Okay, interesting. So, what does it mean? But as long as there are no carry bits. Okay. Then addition boiled down to bitwise XOR. Bitwise XOR plus carry bit. Equivalent to a bitwise OR. Bitwise XOR with carry bit. Since each carry bit triples to the next one ether. Wait a minute. something like this. Oh. Oh, wait a minute. Okay. I mean something like this. Okay. I assume this is the carry bit, I guess. Maybe. The first and only the first full ether may be replaced by a half ether under the assumption that. Okay. The layout of a ripple carry ether is simple, which allows fast assign time. However, the ripple carry ether is relatively slow. Exclusive OR with carry bit. Wait a minute. Exclusive OR. This is the symbol for exclusive OR. Okay, let's try that. This is thing 1 0 0. Okay, 1 0, and then this one. Okay, something like this. This one is 0. Okay. If I understand correctly, the XOR or exclusive OR means that only either one that is correct. Something like this. So if it is the same, then it is 0. Okay. Carry bit. Is this the carry bit? I don't think so. If we do this, right? Come on. I mean, okay. Piecewise XOR. Okay. Where is for carry will be A. Okay. Is this A multiply B? two single binary digit A and B, it has to output sum and carry. Okay, the carry signal represent an overflow into the next digit of a multi-digit. The next digit of a multi-digit. Oh, wait a minute. Yeah, I think this result is incorrect. Oh, wait, but it is n, not addition. Okay. All right. Okay. Oh, interesting. All right. So as long as this is not 0, the add bitwise operation, then yeah, the value does not necessarily mean addition. Maybe something like this. Right, okay. Wait a minute. Addition is basically a bitwise XOR plus carry bit. A bitwise XOR. I think this one, copy that. Oh, is this the carry bit? Mm-hmm. 550. Bitwise XOR. Oh, wait a minute. I think this one, right? Okay, this look. Oh. we got this. Interesting. Okay. It looks like, okay, maybe, oh, wait a minute. Okay, I think something like this, right? Without carry pit. Yeah, I'm not really sure about this. It's a bitwise XOR with a carry pit. And that kind of make me curious, I guess. Whenever the bitwise addition adds more than one, either because the source item or the carry from another place is 1, 2, then the carry is produced and one place affect the other, as long as in an addition that is at most 1 added. These are the same as bitwise. Well, when no carry is produced, elements taking part in circuit are the OR element. Yeah, that make me curious why we use the OR bitwise operation instead of the plus addition. Right. If the result is the same, I guess. Why use bitwise OR instead of addition? Okay. Need the Indian to pick Indian, alright. Is there any advantage of using the addition? It's just a bit slower. That is a big difference when it comes to sum. The numbers, for example. I've answered my own question already, but it would be nice if someone could evaluate. Okay. Addition should use a carry bit to somewhere, or just combine. Even if they sometimes equate, and modern chips are quite efficient in terms of execution cycle. Why do you need to max it with this? Only 0 bits will. Okay. Makes a difference when result is assigned integer. Oh, redshifting it is implementation defined. Using or will, however, invariably produce nonsense. It makes no difference at all when it is unsigned integer. A modern processor executes an add as far as an OR. At least not on modern processor. If the bits being combined aren't overlapping, what the marks on the left hand side as zeros for all bits. On left hand side as 0 for all bits set by the right hand side and vice versa. It's a little confusing. Okay, mentioning to imply that 32-bit value, but the calculation implies a 16-bit result. You will get different result, for example, if you do something like this. Oh. What? Okay. When value already has the bit 7 set. Okay. What is the intention towards the code? And that's the important point. No need to max the left part as incoming bits are zeros. Of assigned integer instead of what is coming in when performing a redshift operation on negative value is implementation dependent. Therefore, portable code should use. So is this the masking is for the negative value? Is that it? Yeah, I'm still not sure. When we use bitwise operation or the arithmetic operation, I guess. Maybe for this one we need the bitwise operation, right? We are calculating in bits instead of the arithmetic. Maybe. And why use them? Let's see. We use a lot more in programming when computer didn't have as much memory in them as they do now. bitwise operators are still used for those working on embedded devices that have memory limitation. The smallest amount of space a variable can take up is 1 byte. The reason for this is that it is the smallest unit of addressable space that a CPU can reference. Even a Boolean that only has the value true and false, and therefore should only take up 1 bit, still used a full byte, and has the remaining 7 bits spaced out. Okay. This isn't great if you are trying to save memory. Most applications have multiple flags, especially those that are referencing physical hardware, to make the most out of the available space. Programmer would combine multiple flags into a single byte. Oh, multiple. Multiple flags into a single byte, allowing them to store up to 8 different Boolean values. It is just what you need if you are trying to conserve memory on a small device. I'm curious because I think open like this, right? There is this, what is it called? Using the bitwise OR for the flag. So I'm kind of curious about that. And maybe this is the reason combining multiple flags into a single byte. Start up to 8 different Boolean values. The one place you may have seen multiple flags being stored is with Unix file permission. Typically, you might see file permission denoted as number like this one. The first number is the permission for the file owner. The second is the permission for the group, and the third is for everyone else. The number tells you whether they have permission to read a file, write to a file, or execute a file. To understand what each number means, you need to convert the number into binary first. 7 in binary is this one, okay. The ability to read and execute. 6 in binary is this one, okay. Which means they have the ability to read and write but not execute. 4 in binary is, okay. So they only have permission to read the file. Interesting. Let me check. Oh, okay. Alright. Oh. So if I do this, for example, 644 with or bitwise operation. Oh, interesting. Okay, so let's assume we have this one. Or okay, 0, and then this one is 1, and it's also 1. Oh, okay. Yeah, this is from the previous information. Add another question. Why use bitwise or why use or bitwise operation instead of yeah, let's do something like this for the question. We can combine multiple flag. Yeah, let me copy this as the reference. Multiple flags into one byte. 8-bit into one byte. For example, in Unix, permission like 44N is this correct? Oh, right. Okay, yeah. I wouldn't recommend this, but yeah, some people enable everything like this. For example, in Unix, file permission, we have flags like this. No, not 6. 4 is flags flag for read. 2 is flag for write, and 1 is flag for secure executable. When we use orbit-wise operation, we just when we combine this flag, we can use the orbit-wise operation to get which flag is enabled, maybe something like that. But yeah, is my representation here correct? I am not sure. I mean, it is the same, right? But what about the other? Okay, maybe something like this. Oh, so regardless or that. But this is only read, right? Not right. Or we are excluding that. I mean, in the Unix file permission, we have, what is it called? Owner, and then think group and everyone, maybe something like that. So 644 is something like this. The permission for the owner of the file, permission for the group and everyone else, if I understand correctly. So maybe if it is for the group, we only combining this one. Maybe okay. We can check the bit. Okay, wait a minute. Okay. If the flag what is it called? Permission for owner, group and everyone. And then okay. Oh no, not is flag for right, and 1 is for executable. Okay, and well, flag for read, binary bits 100 for white, let me put this in here. Binary digit 10, right? And 1. Okay, 1. If alt flag is on, we have bits like this. Width is 7 in decimal. So so we can check if the flag is on or not by using orbit-wise operation like this. Owner become something like this. Read equal 1, red equal 1, and then executable equal 0. And then for the group, maybe something like this. Wait a minute. Oh, 100. Okay. Red equal 1. Red equal 0. Executable equal 0. Everyone. This one still 100. Red equal 1, red equal 0. Executable. Okay, this is my hypothesis, I guess. And what about bit 0? Bits 10, I mean. Like this. Right, executable. So they only have permission to read the file. See, in binary is okay, which means they have the ability to read and write but not execute. For in binary is this one 100. So they only have permission to read the file. Okay. Into 1 byte using or bitwise operation. Okay. Now I can do this, I guess. Okay. Flick for right. Okay. If auto flag is on, okay. One of the benefit of using OR bitwise operation. Alright. Okay. Oh, right. Okay, I guess we will continue translating the virtual to the physical trace with this homework simulation on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.